we can also do the same thing for differential equations. So here I'm going to give you an example of the Poisson's equation. So instead of a linear system, I get, let's say, the Poisson's equation. I have the gradient, I have the divergence of A times the gradient of U equal to F. Alright. And assuming this A is my design variables. Okay, so that is the case where Xun has mentioned of if I have the matrix. In this case, this is like the matrix. If I have the matrix determined by the design variables, how do I do that? And I have J equal to integral over the whole domain of C times U dx. And I assume I have U equal to 0 at the boundary. So the question again is, what is partial J, partial A? Now this is a case we have an infinite dimensional design space, right? I no longer have a finite many of S's. My A is a function of X. A can be any function. And this derivative here is the derivative, is actually a functional derivative. This partial J, partial A by itself is a function. And there is no corresponding direct sensitivity analysis method we can use because it's impossible to be able to perturb any A, to perturb like all the possible A's. Okay, here we are going to use a similar method we used last time. We are going to augment this objective function by something that we know is going to be 0. And what is that? That is the residual of the objective function, A grad U minus F. But this is a quantity that should equal to 0 everywhere. So I should be able to multiply that quantity by a phi and integrate over X and still get a 0. Right? This whole term is going to be 0 because what is in the brackets should be 0. Ooh. Why is the battery running so fast?
Sure.
No, I didn't have it. Okay. So worst case, I can use the blackboard. Okay. Right. So here, what I can do is then, what can do is I can find the phi that removes the term delta U from this equation of delta J. So delta J is equal to integration of C times delta U dx plus integration times phi of divergence of A gradient of delta U, and the phi times F term is fixed. That is, that has nothing to do with the change in the objective function. But now I have an additional term that is phi times the divergence of delta A times the gradient of this original U dx. Right, this term is due to the change in the solution. This term is due to the change in my control parameters. Okay, so now what I can do is I can combine these terms. I want to combine these two terms and find the phi that removes delta U from this equation. How do I do that if delta U is within some differential operators. How can I pull delta U out of these differential operators so that I can say the coefficients multiplied on that is going to be 0? What I want is going to be, I want C plus something times delta U dx, and then plus the last term, which has nothing to do with delta U. Right? How can I combine these two terms into a term that looks like this? Yes, I need to pull delta U out of these differential operators through integration by parts. I actually need to integrate by parts twice in order to pull this delta U out of this gradient and this divergence. The result of that, very interestingly, is going to be divergence times A times grad of phi. Okay, and the adjoint equation is setting this to 0. It's setting the divergence of A times grad of phi plus C equal to 0. So this is very similar to the adjoint equation we get in finite element case, right? So the right hand side is going to be this C instead of this F. Once I solve the adjoint equation, I can compute delta J is going to be, I can perform an integration by parts again over here. We can get delta A times grad of phi dot product with grad of U dx. And I can declare partial J partial A as grad phi dot grad U. That's going to be a function defined everywhere. And that tells me the sensitivity of the objective function with respect to a small perturbation in the conductivity field or permeability field, whatever A is in the physical setting, everywhere. Right? Any questions here? Yes?
So here we have chosen a wave function phi that satisfies the boundary condition, right?
Yes, we also, yeah, right. Also we also need the phi to satisfy at the boundary condition at the boundary in order for the integration by parts to cancel out. In the integration by parts, we are going to discover a term on the boundary that is going to be multiplied, that is going to be phi times the gradient of delta U. Because delta U can be anything, right? We don't want delta U to appear anywhere. And the gradient of delta U does not satisfy any particular boundary condition. So we want to choose phi to be also 0 at the boundary in order to cancel that term out. And the cancellation of the boundary terms gives rise to the boundary condition of the adjoint equation. All right, any questions on this? So all of this we have been doing for steady state problems. Because I think I'm running out of battery, I'm going to do this on the blackboard, but the center screen doesn't go up. Okay. The last thing I'm going to do is look at the adjoint methodology, look at area estimation, and also design sensitivity analysis for unsteady differential equation. When the differential equation has time in it, which is a lot of the problems we're looking at. How does a differential equation that has time in it, how can we do area